Okay, so our topics for today will be quite limited, but they're closely related and quite important. So, the first topic we'll talk about is the concept of flux coupling, which is a way of looking at flux variability, or how the solution space for a given metabolic model looks in a way that's a little bit more detailed and a little bit more representative than what we've done earlier with, for instance, FVA, or flux variability analysis. After that, we're going to try to tie that in to how we can engineer an organism to create the maximum possible amount of a desired byproduct. And we're going to follow that up with a MATLAB example on how this is going to be done. This MATLAB example is going to be a bit simplistic. Normally we would be doing this using something called OptNock, which is a bit more of an advanced tool that we will be talking about in the future. But I think that as an initial example, doing things a little bit more by hand, but keeping it simple, is beneficial because it gives a better understanding, hopefully, of what's going on under the hood, rather than just resorting to this sort of black box tool that is quite thorough, but you might not truly understand what's going on underneath it. So, before we talk about flux coupling, we sort of want to put it in context relative to FVA. So FVA, that we talked about quite a bit before, it's a way of looking at the variety of solutions we can have for a given optimization problem. So typically when we optimize, we're going to find that there is no single optimal solution, but rather a sort of an optimal solution space, which can be as many dimensions as we want. For example purposes, we typically restrict it to 1 or 2 dimensions. So here, for instance, we have a very simple solution space. We have V2, which is the flux that we want to optimize, and then V1 is another flux. And our solution space looks something like this. And with FVA, what we can do is we can identify the span of fluxes V1 that is compatible with an optimal value of the objective function. So if we see here, this whole upper surface corresponds to to the optimal solution, and we see that V1 can span a certain amount of of values over this. Right? It has a lower bound and an upper bound, and this can be quite useful. In fact, it is very useful, as we'll see for metabolic engineering, as we'll see later. But it's also somewhat naive, because when we do FVA, we'll find a span, but that is really only looking for that reaction in isolation, and we can't really combine that over multiple reactions to get a good impression of the solution space. To explain, for instance, imagine we have this simple solution space. We have V1 and V2, and then we're optimizing in this direction Z, and it might not fully line up with the picture, but let us suppose that our optimal solution is this whole like slanted line here, right? And if we do FVA, what we'll find is that the optimal value for V1 will follow this span here, because that is like the coordinate span of that line. And same for V2 with the other axis, we're going to have this as like a span for V2. Now, if we were to combine them, that would give us a sort of optimal solution space of this red square. And that isn't accurate, because this red square does not describe the optimal solution space, which is instead our dotted or dashed line here, right? Because our upper right corner, that is outside of the feasible space entirely, while our lower left corner is non-optimal. And so essentially this relationship between fluxes in a given state is something that's not captured by FVA. FVA is very isolationist in that sense. Instead, we can do something we call flux coupling analysis. And so with flux coupling, what we're doing is we want to account for certain types of relationships that we find in a metabolic model. And you can arguably generalize things more than this, but at an initial level we'll talk about three main categories that we're looking at in terms of coupling. We have what we call directional coupling, which, as it says here, if a non-zero flux for V1 implies a non-zero flux for V2, but not necessarily the reverse, which means that if V1 is non-zero, V2 is also non-zero, but if V2 can be non-zero while V1 is still zero. Then we have partial coupling, where a non-positive flux or a positive flux for V1 or V2 means that the other also has a net flux, but there is a certain variability in their ratio. And lastly, we have what we call full coupling, where essentially these fluxes through V1 and V2 would be proportional to each other. That is, that for a given flux V1, only one other possible fixed flux V2 is possible, and for a given flux V2, only one other flux V1 is possible. We can also look at, lastly, outside of this, we also have this notion of non-coupled reactions, which is anything really that doesn't fall into these categories. So how would this look in practice? So let's start with the uncoupled case, just as a baseline. So here is our model. I have not labeled the reactions. Instead, I have provided just a list of reactions at the bottom. So we have two independent import reactions for M1, two independent import reactions for M2, and then we have one final reaction, R5 here, that merges M1 and M2 into biomass. So what we get here is that if we call this upper one here V1 and this lower one here V2, V3. So V1, V2, V3, and V4. Of course, M1 and M2 need to be produced in a fixed ratio, but M1 has two alternate ways it can be produced, as does M2, which means that for any value of V1, we have a certain variability in what is the value of V3 that can be used. Because we can imagine that we have all the flux going through V1 and all the flux going through V4, and so there would be no flux through V3, or we can have flux through V1 and flux through V3 in equal proportion, or we can have flux through V2, none through V1, and then whatever we want here between them two. Like there are a lot of degrees of freedom here that can be satisfied, and we can have any scenario with both V1 carrying flux and V2 not carrying flux, V1 and V2 both carrying flux at the same time, or sorry, V1 and V3 both carrying flux at the same time, or the other way around. All this while still satisfying optimality, right? So for a reaction system like this, our solution space would look something like this, and that would correspond to the uncoupled case, where we have where we don't really have any fixed relationship between V1 and V3. On the other extreme, we have this fully coupled case. Now we only have one import reaction for each metabolite M1 and M2. While they still combine in the same way as on the previous slide, with M1 and M2 together forming into M3, and then that M3 is turned into biomass. I've added this like intermediate reaction, M3 or intermediate metabolite that's turned into biomass, because it allows us to show the different forms of reactions that will give us sort of topological relationships that will give us a fully coupled pair of reactions, because they can happen in multiple different ways. So if we see here, M1 and M2, as previously, need to be produced at a fixed rate relative to each other. But now, since they only have one reaction producing each of them, then those reactions are necessarily locked at a fixed rate to each other, because we don't have a choice here, and the stoichiometric coefficients in reactions for these metabolites, or any product of them downstream, will sort of lock them into being produced at a rate fixed relative to each other. And that is a good example of something that causes a fully coupled reaction pair. Alternately, if we look here, for instance, at this reaction R3 here, which takes M1 and M2 and turns them into R3, the mass balance constraint on M3, since it only has one outgoing and one ingoing reaction, will force R4 and R3 to be directly coupled to each other. As for that matter, we see that R1 and R3 are directly coupled to each other by the fact that M1 needs to be mass balanced, right? It needs to be produced at the same rate by R1 as it is consumed by R3. And that will create a direct coupling between them. In terms of solution space, it gives us a very simple solution space. Here, in fact, we will see that, for instance, V1, V2, which would be this flux here and this flux here. That was the first one we're talking about. They're going to just, like, the feasible solution space for them is just going to be on a line. No matter what other fluxes we have. Now we're not really forcing optimization, but that is not necessary. We see that, yeah, V1 and V2, they're forced on a line against each other. There's no flexibility. There are no degrees of freedom for what V2 can be given a certain value V1. So this here is going to be a constant rate. And we would see this if we plotted, for instance, V1 here against V3 or against V4. Everything here is coupled to each other for various reasons. Either because you have stoichiometric coefficients on the reaction M3 that require that M2 and M1 are produced at the same rate, or the mass constraint of M1 that means that M1 needs to be produced by R1 at the same rate is consumed by R3, as we have similarly R3 and R4 need to match because M3 needs to be mass balanced. And the thing with fully coupled relationships like this is that since they are so strict, they're also very strictly transitive. If if R1 and R2 are strictly coupled, fully coupled like this, and R1 and R4 are also fully coupled, then necessarily R2 and R4 will have to be fully coupled as well. And this will apply to any indefinitely complicated set of reactions. If any two reactions that are fully coupled, if you have two reactions that are fully coupled, and reaction A is also fully coupled to a third reaction C, then reaction B and reaction C will be fully coupled as well. And that is something that's quite characteristic to fully coupled reactions. Okay, let's move on to the intermediate cases. So we have here a case of directional coupling. Here, our model is still quite simple. We have two metabolites M1 and M2 that can be imported directly. Either of them can be converted into M3, either through this upper reaction here or through this lower reaction here. We see that M2, M1 can be turned into M3 by this reaction 3, M2 can be turned into M3 by this reaction 2. So now it's not like on the previous slides where these two combine to form M3. Now they can just individually convert into the directly. So we don't have any stoichiometric lock between the production rates of M1 and M2. Meanwhile, what we do have is we know that if M1 is produced, then it has nowhere to go but into M3, and M3 has nowhere to go except into biomass. So what we see here, or similar, like, yeah, if it is important to R1, an activity through R1 implies that you need to have some activity through R2, and so on. And what that means is that if we have this activity, then the reaction M3 to biomass, R5 needs to be positive. I actually mislabeled the axis here. This should say V5. But what we see is that our valid solution space sort of has this triangular shape. It doesn't need to be strictly triangular like this. The key aspect here is that you have this line here, and that your solution space is above and to the left of that. This upper bound here, we could have something else. We could have a line that looks like this, or looks like this. Anything that's concave, right, would be valid. But we would have directional coupling, because what we see here is that if we can have a flux through V4, or in this case actually R5, we can have a flux here without a flux here. That is possible, because we could just have precursors produced through the slower pathway instead. But we can't have the other way around. We can't have a flux here without also having a flux here. And this is a case of directional coupling. Directional coupling is also transitive, but it only goes one way, and it's typically something that's formed by this sort of branching relationship. If we'd had another sort of like branching flux upstream here, then we would have directional coupling between R5 and whatever other reactions are up here. So if R1 is directionally coupled to R2, and R2 is directionally coupled to R3, we still also have this directional coupling going in this direction. But it wouldn't necessarily be the case in the going backwards in the other. The important thing to note here is that when we're talking about directional coupling, we're not really talking about the direction of the fluxes. Because you could also have something as a directional coupling relationship where that would go the other way around, where, because what we see here is that as we move in the direction of flux, our pathways merge, right? And it's this branching and merging that causes directional coupling. We could imagine that we start with one metabolite, and as we move along the metabolic stream, instead of merging here, instead that one pathway would branch out into several multiple pathways, and there we would also have directional coupling, but going in this case in the same direction as the flow instead of going in the opposite direction of the flow as we have here. The last case we have is partial coupling. Partial coupling is a bit trickier because for it to happen, you often need to have a model that's a bit more complicated than what we use in our examples. But imagine we have the following. This looks a little bit arcane, but let's explain. So here we will have our metabolite M1, which is imported by reaction R1. And then M1 can be converted into M2 by, or can be used to produce M2 by one of two reactions. Either this upper reaction here, R3, or this lower reaction here, this upper reaction here, R2, or this lower reaction here, R3. In either case, we're going to have a byproduct of M3. The difference is how much of it we have as a byproduct. So if we go through this upper one, we're only going to produce one M3. If we go through this lower one, we're going to produce two M3. And in each case, M3 can just be secreted outright. As we see here, like R5 is the transport reaction for M3, just secretes R5. So both this arrow here and this arrow here would correspond to the same reaction, R5. If we now plot V1 against V5, so this against this and this, because this and this are the same reaction, they're just labeled in multiple areas to sort of show that we can have two different reactions. What we see here is that if we have a flux through R1, some amount of M3 will be produced, and therefore will also have to be secreted. But depending on which pathway is used, and both of these really are valid, then we could have a varying amount of it. And in terms of the flux space, it will look something like this. So we will see here that at 0 we just have a point, so a 0 flux of either means that the other is also 0. And a non-zero flux of either also means that the other is non-zero. And that is symmetrical. But we don't have this fixed line as we have in full coupling. So it's sort of an intermediate regime as well. And this is what we call partial coupling. Another way we can sort of represent all these cases at once is by this sort of schematic here. So here, R's are essentially ratios between flux 1 and flux 2. So for instance, this line here would, since it's a line going through 0, would correspond to a constant R. While this vertical line here would be R equals infinity, this horizontal line here would be R equals 0. But any given line in the solution space would correspond to a constant R. So what we can do is we can formulate this R and then do that R as an optimization problem. We can both try to minimize it and maximize it for a given model with a given set of constraints. And so that we'll find an upper and lower bound on it. And since these R's correspond to lines on our solution spaces like this, and so on, identifying the span for R will also be able to give us a general shape of this solution space. So for instance here, if we have this directional coupling, we have R min equals 0 and R max equals C, which is a constant. And that means that our solution space has to lie within the cone, so to speak, or infinite triangle that is delimited by this R min equals 0 line, which would be here, and a finite R line, which would be here. And so that would be like you can that gives us that that will be what we find by this optimization problem. We're not going to find where this triangle ends, but what we'll do is we will find sort of the spans of it, like how far in this direction does it go and how far in this direction does it go, like how wide is this angle that's described here. We don't really get to know how far it extends, but that is not too relevant right away. Similarly, with partial coupling, we get that same thing, except that in this case we don't have both R min and R max are finite and non-zero, which means that our triangle is bounded by lines, or our solution space is bounded by these lines here and here, but that are not on our axes. We can have in the fully coupled regime, then we see that R min and R max are one and the same, and just a constant, which means that the bounds here actually coincide into one single line. And then we have essentially this regime here, right, which is the fully coupled regime. Similarly, directionally coupled, just the other way around, would correspond to the same here, because we would just be reversing the reactions, and that would be the same as when we're reversing the reactions, the ratio would be the same as just 1 divided by this. So if we look, for instance, at partial coupling between V1 and V2, we get R min C1, R max C2. But if we did it the other way around, we would get R max equals 1 divided by C1, and R min equals 1 divided by C2. It's similar here. If we take here, we just reverse it, and we would get, since R max would be finite, R min would be 1 divided by the same finite number. Meanwhile, R max would be 1 divided by this R min, which would be 1 divided by 0, which is infinity. So that would be what we find from our optimization problem. Well, in the extreme case, when it's uncoupled, well, then our boundaries here are on the axes. There is no restriction, and so our R min and R max would be 0 and infinity, respectively. So how would the code for this actually look? Well, first you aggregate all duplicate reactions and merge them. Then you try to find for each flux what the maximum value it can carry is. If that value is 0, then the notion of coupling doesn't matter, right? That reaction is blocked for the entire model and it can't carry any flux. So we're just going to throw that away and disregard it. And then what we do is for every pair of reactions, so for first have loop j to m, or j to m minus 1, and then that's our first reaction, and then from that we're going to do j prime equals j plus 1 to m. So we're going to essentially be filling out like the upper half of a triangular matrix. And we optimize R min and R zero, R min and R max. And then just depending on what our outputs are, R min and R max relatively, we will throw them into these different categories of coupled and or uncoupled or partially coupled and so on. So that is typically how this sort of would be done. So if we look at this model here, what we would find by doing by going for flux coupling finding is we would identify this sort of backbone here as fully coupled. V4 would be blocked. The remainder here, I'm not quite sure if they would be uncoupled or partially coupled. It would depend a little bit on what you're looking at. But all of these here would be fully coupled to each other. Not only would V5 be fully coupled to V6, again because we have this this constraint that C needs to be mass balanced, but also we have that since VE and V7 are fully coupled, V6 and V7 are fully coupled, then V6 is fully coupled to VE as well. Any combination of these 5 reactions are fully coupled to each other, because we have here VBio is fully coupled to V6 by the fact that VBio is fully coupled to V5 and V6 is also fully coupled to V5. So that's how V6 and VBio are fully coupled. Since V6 and VBio are fully coupled here, that means also that V7 will be fully coupled to V6, because if this input is fixed and this output is fixed, then this output here, V7, will also have to be fixed. This is actually a little bit more of a complicated example than what we've looked at earlier, but it shows nicely how this notion of fully coupled reactions really is something that can reproduce downstream. And so coupling can often be a very indirect property that isn't necessarily apparent from just looking at a metabolic model or a metabolic map outright. But that also means that for a given model, a minor rewiring can actually have a pretty substantial effect on coupling of reactions that are at first glance really quite independent from each other. And similarly, an interesting thing with coupling is that it shows us it shows us what are essentially equivalent knockouts in terms of reactions. Because as we've said here, this full coupling indicates that if V5 is 0, then V6 also has to be 0, right? If V5 is non-zero, like if V5 is 10, then V6 also has to be something. Let's say it has to be 10, right? But if V5 is 0, then V6 has to be 0, V7 also has to be 0, VE has to be 0, and so on. And what that means is that knocking out V5 is the same as knocking out V6. And this can actually be quite useful for us if we want to do multiple knockouts and we want to simplify our search. Because if you're going to have a model with 1,000 reactions, you have to do 1,000 separate knockouts. If instead, if you want to do all single knockouts, if you want to do double knockouts, you have to do 1,000,000 knockouts in theory, if you're going to be a little bit exhaustive and brute force about it. But if you identify fully coupled reactions, then you can essentially group them as a single group for the purposes of knockout studies. So essentially what you can do here is you say, oh, V5, V6, V7, all these are equivalent knockouts. And so if you're going to do a quintuple knockout, which would be far too time consuming to do normally, well, maybe you can do it by just saying, okay, we don't have to try all the combinations of knocking out V5 and V1, V6 and V1, V7 and V1. If you know that V5 and V1 have a given effect, then you don't need to also check what the V1, V6 mutant takes. So flux coupling can be quite useful in that respect, especially if you're going to do higher order knockouts. So, in what might be initially a bit of an abrupt change of topic, but it will sort of relate somewhat into this flux coupling, especially as we continue with it in further lectures, is the topic of metabolic engineering for byproduct production. So, again, so far we've mostly talked about using a model to predict the behavior, or to chart, to predict, and to understand the behavior of the cell. But one of the key purposes of a model is design. That essentially we want to do modifications or figure out what modifications we can do to our model that will have a desired result. And we looked at that in part with looking at gene knockouts just in terms of viability. If we knock out a cell, or sorry, if we knock out a gene, will the cell still be able to grow? Like at all, or what will be the growth rate? And that can often be useful, for instance, if we want to look at chemotherapy, for instance, because one of the hardest challenges of killing cancer cells is not killing everything else in the organism. Killing cancer cells is very easy. You can do it with a flamethrower, but then you would also harm the rest of the organism. That's undesirable. So an application for this sort of just growth-oriented gene knockout analysis would be, okay, identify genes that would be essential to the cancerous cell but non-essential to the healthy cell. And those could then be targeted by some form of drug. That would be an application of that. But that is a reasonably niche use, and it has other challenges. The main application in terms of testing and design that we can use for FBA is to identify strategies for optimal production of a desired byproduct. So imagine this following model here. We have import of metabolite M1 through this R1 here, and then this M1 can be passed into a variety of pathways, each of which has the ability to produce biomass, but some different things happen in between, and they will convert M1 into biomass with varying levels of efficiency. Meanwhile, we have our metabolite MT for target. That's what we want to produce, right? The cell wants to produce biomass. We want to produce MT. And we have these reactions that can do one or the other. So this upper pathway, we just have M1 is turned into 3 M2, and then each of those M2 can be turned into 1 unit of biomass. So here, 1 M1 is turned into 3 biomass, straight and very efficiently. In this middle pathway, we see that M1 can be turned into 2 M3 here. And then that M3 can be turned into 1 unit of biomass, either with a byproduct of M4 or a byproduct of MT. But this pathway is somewhat less efficient in how it converts M1 into biomass, because here we can get 3 units of biomass for every unit of M1. Here we only get 2 units of biomass for each incoming unit of M1. And then we also have M4 and MT as a byproduct. And lastly, we have our lower pathway here, where M1 is turned into 1 M5, which in turn is then turned into 1 unit of biomass. But this transition from M1 to M5 will also produce MT as a byproduct. So it would be obvious here that from a cellular perspective, the cell would optimize into using this upper pathway, right? because that is what it's constrained by. If we assume that its constraint is only how much M1 it can absorb, then if it wants to grow as fast as possible, it wants to convert M1 into biomass by the most efficient pathway it has to do that, and that is through M2. And if we map out our solution space here with V9, which is the biomass secretion, and V8, which is our production of MT and secretion of MT, our solution space will look something like this. For low growth rates at a given constraint of M1, then we can produce M5. We can produce MT, right? So the most efficient way of turning M1 into MT would be through this M1 M5 pathway. And so, or no, actually, the most efficient way would be through M1 M3, and then because here you can get through reaction. Reaction 6, which turns M1 into M5 plus MT. We get 1 unit of MT for each unit of M1. If we instead have M1 to M3, we get 2 units of M3, which in turn can be used to get 2 units of MT. So in this pathway here, we would actually get 2 units of MT for each unit of M1 that comes in. But in either case, if we're gonna, and that would work for a certain amount, right? We could produce MT at a given rate here, as the growth increases. But if we want to be at this point here, right? We're growing as fast as we can using this pathway. But that is not the fastest cell can grow. The fastest cell can grow is using this pathway, and so the cell will optimize and use this pathway less and less, and this pathway more and more. And instead we'll go here, and this will be the optimum for the cellular objective, which corresponds to 0 production of our engineering objective, right? And this is the challenge at hand, is that fundamentally our goals, our interests, and that of the cell are not aligned. So the question is, what can we do to fix that? Well, what we can do is we can make mutations to reshape the solution space. And we want to reshape the solution space essentially in such a way that that the production of the engineering objective and the production of the cellular objective are coupled. So here, right, the V8 and V9 are fully uncoupled because they can both be 0 and while the other is positive. Actually, this is not quite accurate because any production of MT will actually require some production of biomass. So this line here should in fact rather be something like this. Our triangle should actually look more like this. But this upper part here is the most accurate, and that's the most relevant for our engineering problem, because this point here is where the cell is going to converge, and that will do us no good because they will not produce anything of our objective. So what can we do? Well, let's knock out this upper pathway, right? That most efficient pathway, because that isn't helping us. What will happen now? Well, we still see that for the purposes of producing biomass, this, what was the middle pathway, what is now our upper pathway, was the most efficient, right? This here is really a bad pathway for the purpose of growth, and the cell really doesn't want to do that if it can avoid it. So it's going to turn here, and then we're going to have M3, and then M3 can be converted at a 1-to-1 rate into biomass by either this upper reaction or this lower reaction. And that is going to be, and that's going to be at the discretion of the cell, right? So we can have an optimal solution that either has all the flux through here, or an optimal solution that has all the flux through here, or any combination of that. And in terms of solution space, we would have something that looks like this. Again, our reactions here, V8 and V9, are the same. Our objectives are the same. It's just that now we've reshaped the solution space, right? We've essentially cut off this part here, and we've sort of readjusted our scales a little bit. But we cut off this part here. Now, instead, our optimum for the cellular objective is along this line. And here, it is in fact possible to both have production of our desired metabolite, our engineering objective, is produced at a certain rate, while also the cellular objective is being satisfied, because this is what's going to happen, and this is what we want to happen. And so, this is where the cell is going to be. The problem we have here is that here we're also still fully decoupled. Again, no, this would actually be a directional coupling, because as previously this upper line here is inaccurate, we should in fact have a line going diagonally like this. But again, that is less relevant. The most interesting thing is this optimal surface here, where the problem that we have is that, okay, now the cell is capable of satisfying our objective and the cellular objective at once, but we have no guarantee that it will, right? And it is quite possible that the cell, it evolves until it reaches this point, and once it's there, it's happy. It doesn't care what we want. It's not that smart. I mean, it doesn't even care what it wants. It's just that if it grows, if it satisfies its objective, it gets to continue. Our engineering objective is not something that works, or that the cell takes into account. Arguably, we could say that, oh, we could selectively breed it in order to satisfy our engineering objective. But if you're going to try to do selective breeding of microorganisms, you're in for a tough time. So, well, what can you do then? Well, can we try to reshape our solution space even more? Well, let us now knock out this upper pathway by an appropriate mutation. What happens then? We're stuck now with yeah, we're stuck now with only this. Right? This is the only pathway we have. And this is a clear case of direct coupling. Right? Because this is R6. This happens at a fixed rate. R6 and R7 are also directly coupled because of this constraint on M5. And so it comes from this that any production of biomass necessarily also requires proportionate production of our target metabolite. And so if we were to mutate our organism into this capability by knocking out its other capabilities, sure, it's going to grow slower than it would in the wild type. It's not going to be able to grow as efficiently as it wants, but we're not looking for a fast-growing organism. We are looking for an organism that is going to reliably produce MT. And this organism, if it's going to grow, which is what it's going to try to do, it will necessarily have to produce MT. Right now, our engineering objective and a cellular objective, they're satisfied at the same time. Any point in our solution space, which again now is just this line, where we'll optimize for both at the same time. We've reconciled our engineering objective with the cellular objective by an appropriate set of knockouts. And so the question is, for a model, we want to identify these knockout strategies that can do that. This strict, direct coupling like this is not strictly the only thing that we'll be satisfied with. Imagine if instead our pathways looked like this, where we also had M1 can be turned into MT directly. Then our solution space would be looking something more like this. Now we would have directional coupling, but this is also fine because, sure, the cell would be able to produce more here, but the most important thing is that we need to reshape this here, the solution space, into such a shape that production of the cellular objective, or satisfaction of the cellular objective, provides us at least some amount of the engineering objective. Ideally, of course, we want to identify the set of knockouts that will push this this line here as far up as possible, where the optimal solution, which in this case would be here, is the most in line with our engineering objective. And in terms of doing that, well, how would we actually do this in practice? What we would do is just try as many knockouts as we can and then see which one performs best. That is somewhat similar to what we do when we do gene knockouts, is we just try as many combinations as we can. Of course, there's going to be quite a lot of combinations possible. Single knockouts can be done quite easily, while double knockouts take more time. Essentially, what you're doing here is you're identifying an FVA problem for the cellular objective. So you'll set your engineering objective as that's an identified reaction. And then what you do is you identify your cellular objective, and then you do FVA for the engineering objective. So this is the same in computational intensity as doing a single gene knockout or double gene knockout. And so, of course, the more knockouts you want to try, the more time it takes. But there are some shortcuts to do that in terms like more efficiently, and that would be covered by the OpNock framework, which will be a topic for another day. I think that now it's a good time to sort of move into MATLAB and sort of show how we would do this kind of metabolic engineering in practice in a rather simple example. Okay, so we're back here in MATLAB. As you see here, we've loaded Cobra Toolbox, and we've loaded in our model file, which is going to be our standard E. coli core model that we used in the last lecture as well. As we see, it's pretty small here, but you should hopefully be somewhat familiar with this by now. To begin with, we can do just the standard optimization for it. So we'll do optsol equals optimize CB model. See here, it grows nicely as we expect. And then if we look at the optsol here, if we look at the fluxes, these are our wild-type fluxes. Now, the exercise we're going to do now is we're going to identify how we can force E. coli to produce ethanol as a byproduct. We all know that yeast is a good example of sort of metabolic engineering, but in a rather traditional way. It wasn't really figured out by FBA, but rather by good old-fashioned trial and error, or by accident, where what was discovered is that if you constrain yeast by starving it of oxygen, then what you're going to do is you're going to force it to use pathways that will produce ethanol as a byproduct. And that's something that we already know. And we could have done that with a yeast model here in Cobra, but that would take too long for an example like this, because most yeast models are a bit bigger, and so any sort of like engineering analysis like this would take a little bit longer than we want to do in this video. So instead, let's try to see if we can find a way to make our E. coli be forced to produce ethanol as a byproduct. So if we look here at the reactions in our model, we have model.reactions. We have here at 24, that's X ethanol, right? So if we look at our flux vector for the wild-type optimal solution at 24, that's 0, right? Our E. coli model under normal wild-type scenario is not going to produce any amount of ethanol that we can appreciate when it's optimizing for growth. So let's just double check that that's true, because this is just one of the solutions. Maybe it's possible for the wild type to produce ethanol under normal conditions, but just that is also possible for it not to, in which case we'd still want to do something about it, but at least that would be interesting to know. So let us do FVA min wild type, FVA max wild type equals flux variability model. So here, and then we look at 24. So if we look at FVA min, that's the lower bound. Of course, that's going to be lower than 0. It's going to be 0 exactly. So it's never going to absorb ethanol in the wild type, but yeah. If we look at max, which is what theoretically what maybe it could secrete, we see that we get 1.2845 times 10 to the minus 5, which is a very small amount. It's probably, this might very well just be a float point approximation error that we'll get in Cobra every now and then. But even if it isn't, this is a negligible amount. This is not an appreciable amount of ethanol that we can produce as a byproduct. So the question is, can we do a gene knockout that will force us, or that will produce a certain amount of ethanol, or that will force the cell to produce a certain amount of ethanol? So let's try this out. So I've made this little script here, coupled growth, that goes as follows. So our model consists of n genes, and our reaction that we want to optimize for is secretion of ethanol 24. That's our engineering objective. This is not the cellular objective. We're not touching the cellular objective. This E. coli cell is still going to try to grow as much as it can. So we have our 137 genes, and what we're going to do is we're going to try to knock these out, in each of them individually, and see what happens. So we'll loop through each gene, and then we'll create a duplicate model of our E. coli, which is the same, just that that specific gene has been deleted, right? So here we just take, at each time we take model, delete gene I from it, and then assign that to KO model. Then we optimize it once, just to see that it solves. If you did not have this, like for some of the knockouts, you're not going to have any feasible solutions. Not even that the optimal solution corresponds to zero growth, it's that the solver will not be able to resolve it. Essentially, is that with those mutants, there is there is no way of satisfying the constraints and the stoichiometric coefficients at the same time. So if you don't do this test that it can actually solve before you go on, then you're going to get some errors because MATLAB doesn't quite know how to handle when that returns. So we're going to just check, okay, can that mutant grow at all? And if that mutant can grow, or at least if it can be solved, you can still have it solved and then just solved for zero growth, which would still return optimal, but that is fine for our purposes. And then first, we write down our optimal solution, just to keep it around. It can always be useful. And then what we'll do is, for that mutant, we'll run FVA. And so we're going to be running an FVA over the whole organism, or over all the reactions for that single mutant. And then from that, we will identify, for our specific engineering reaction, 24, what is the minimum production of, or minimum flux from FVA for that reaction for that mutant. And similarly, the maximum value for that mutant. And then we're just going to write that down. And so here we're going to end up with min-prod, which is essentially the minimum production of ethanol compatible with optimal growth for that mutant. And here's going to be the maximum production of ethanol compatible with optimal growth for that mutant. So let's run this and see what that gives us. It takes a little while because this is essentially the same as a double knockout. I could have just done the flux variability for that one reaction we're looking for, and not for all of them. That would have been a bit faster, but then we'd need to throw in a bunch more arguments, and I was a bit lazy for this. This doesn't take too long on this model. Right, here we're doing essentially the equivalent of a double knockout, while in if you're being efficient about it, you only have to do the equivalent of whatever knockout you're doing here, right? Here we're only investigating single knockouts. We could loop this twice over, and then loop over the genes a second time, and then delete 2 genes at a time, identify the fluxes there, and so on. So this takes actually a bit longer than it did when I ran this the first time, but that's fine. Okay, so this is finished running. And so we want to identify which mutants. We can start with looking at this min prod here, because that's going to give us the lower bound for production of ethanol for that given mutant when it's growing optimally. So if we look here, it's mostly 0, which honestly is to be expected. Can we find anything here that isn't? Well, here we have a little bit of string, 63 through 75. All these mutants will have to secrete ethanol. And let's continue looking here a little bit more. 137. So all these mutants here, 63 through 75 and 137, they will have to produce ethanol in order to grow. Let's see how well they grow relatively, because it might be problematic for our purposes if these things produce ethanol but they grow at 1% of the wild type rate. Then we can't really sustain it in the lab, and that wouldn't be valid. So let's have a look. Then we can look at our variables. Where did we write that down? We wrote it down as ko-op-dreg. Ko-op-dreg. So if we look here, most of these mutants really aren't essential. So yeah, we would expect most of them. If we look here, I think it was 63 through 75. They grow at 0.2117 relative to a wild type of, I think, 0.8739. So they grow at about 25% of a wild type, as does the 137 mutant, which is a substantial reduction. But that is still acceptable. Growth at a quarter of the wild type is typically compatible with life. And so, yeah. What we find here is that if we just do now find min prod above 0, this returns us these genes. So you can do model.genes min prod find, and all these single mutants here would be expected to produce ethanol when they are growing on our default medium. So this is an example of the sort of analysis that we can do with in terms of looking at metabolic engineering. It's essentially how it's how we can identify modifications done to our organism to force that organism to satisfy our engineering needs. And yeah, no, it's this is the basic gist of it. There's a little bit more that can be expanded on it, especially in terms of being more efficient at identifying knockouts and getting a more detailed overview of what we can expect in terms of production, and maybe making the production as consistent as we want. Because if we look at, we can find, for instance, if we just look at max prod directly, this is often just rounding errors, but let's look at prod find min prod over 0. So what is the max production? If we just compare, yeah, so we find actually that for all of these mutants, they will produce ethanol at a pretty fixed rate. So in this case, it's fine. But often you can have pretty large spans here, and that might be undesirable. So you want to get a bit of a better overview of how much of your byproduct is going to be produced for a certain production rate. And then we're going to be talking about production envelopes and so on, but that is for a later time. I think this now is a good place to stop and just keep in mind how this approach can be used to, in a sort of quick and dirty way, identify mutations we can do to satisfy a given objective, which in our case here is producing ethanol from E. coli.